Hello, everyone. You are welcome to today's meeting. And in today's meeting, we are going to start the topic sets, and we'll concentrate more on what the core math aspect of sets, because this is a core math meeting. Okay, and by the end of the lesson, every student or the student should be able to or should know all the concepts associated with sets. Okay, that's the general objective. And the particular objective, you should know what radical expressions are, what a set is. Okay, and you should also know the various types of sets. You should know the how to reduce sets in its basic form or to its basic form, or how to write set in its basic form. And equally, you should be able to perform basic algebra on set. You should be able to add, you should be able to subtract, you should be able to divide and multiply. Okay, set. Okay, and that is going to be our target, okay, for this or today's meeting, this morning's meeting. So quickly, let's go and look at what a radical expression is, or what radical expressions are. So these are mathematical expressions of the form nth root of a. Okay, nth root of a. And the n that we have here is what we call the index. Okay, and the a that you have there is what we call the radicand. However, the symbol that you see here is what we call the radical sign, radical. So you can see that the name of the expression comes from the name of what? Of the sign. So radical expression, this is a radical. Okay, so for a radical expression, okay, you should know your n can be any value, but usually we use, okay, integers, positive integers. And we'll always say that it will be greater than 2. So your n, okay, must be greater than or equal to 2. That's why you have, okay, the square root, okay, of maybe a. In that case, usually if the square root, we don't write it, that's a special situation. So we write this one as root of a. However, we know that our index is what is 2. Okay, and the number that you have under the radical sign is called the radicand. Okay, so for your expression, your radical expression to be termed as a set, okay, we should have a particular condition satisfied for n and as well as what your a. So let's quickly go to, okay, the definition for a set. Okay, so sets are special forms of radical expression. So they are special. So they are still radical expression, only that because they are special, you've given it the name sets. Okay, of the form, okay, you can see root of a and the square root of a. Usually you write root of a, where n, which is your index, is equal to 2. And your a, which is the radicand, is what? Not a perfect square. Okay, so your radicand must not be a perfect square. So if you have any radical expression of the form, let's say I have 3, okay, let me use square root of 3, square root of 4. Okay, if you look at this, you can see that our n obviously is equal to 2. Our a is equal to 3 here. If you come to this, your n again is equal to 2. Your a, which is the radicand, is equal to 4. Do you agree? My professors, yes. Do you agree? However, let's look at the first one. The first one, you can see that the first condition is satisfied. We said our n must be 2. The second condition, which is the a, okay, the a must be a non-perfect square. And obviously 3 is not a perfect square. You should know your perfect squares. Okay, you know the perfect squares will be 0 is a perfect square, 1 is a perfect square. So the squares of, okay, the integers. Okay, so 1 or positive integers, let me put it that way. Okay, 1, okay, 1 squared will be 1, 2 squared will be 4. So 4 is a perfect square. You know that you did that in JHS. So 9, 16, 25, what have you. Going forward, okay, you have a slide with that definition over there. So the first one here, Just per the definition of what? Of a set. This is a set. However, if I come to this, my n, okay, is 2. So the first condition satisfied. My second, this one, both conditions were satisfied. Okay, n is equal to 2. Your radicand A is an unperfect square. However, A, which is equal to 4, is 4 a perfect square?
Yes.
Okay,
Yes,
so
please.
once this is a perfect square, the second condition is not satisfied. So it means this is not a set. Okay, this will rather give us what? 2. And for sets are always irrational numbers. Okay, irrational. However, you can say the root of 2 is not, okay, irrational, it's rational. So take note. So example, root of 2, root of 5, root of 12. Obviously, 2 is not a perfect square, 5 is not a perfect square, 12 also is not a perfect square. All of them, they have the index, okay, to be 2. Okay, and take note, multiples of sets are also sets. When we talk of multiples of sets, okay, let's say if I have multiples of 2, what does that mean? Or multiples of x, it means maybe x times 2, x times 3, x times 4, x times, you get the point. Or we can say that x times x, x times, is step 3 times. But usually when you say multiples, we are talking about what? Numerical multiples. So in this case, if I have root of 2, okay, I can have 2 roots of 2 as a multiple of what? Root of 2. I can have 3 roots of 2 as a multiple of what? Root of 2. So this being multiplied by 1, which is the original one, multiple will be 2 times this, 3 times this, 4 times this, what have you. It's my point well made. So it means if this is a set, okay, whatever its coefficient is, it will still remain a set. Okay, if what you have here is a set, multiples of that, which will be 5 times this, will also be a set. So if you want to determine a set, okay, remember, we don't use the coefficients. Okay, we said we use the index and the radicand. So irrespective of the coefficients, okay, if what you have here is a set, it will still remain a set. So take note of that. Okay, quickly, let me move on to the types of sets. Okay, for some of them, I will be very brief. Okay, so pure sets or complete sets. Okay, a set which has only one as a rational factor, the other factor being, okay, irrational. That is a set with a coefficient of what? Of 1. So you can see that if I have x, I'm just using, okay, let's say A. Assuming I have A. Okay, how many factors do you see in this expression A? How many factors?
1.
One factor. Basically, in actual fact, it is 2. But because 1 is a factor of every number, we don't consider it as a factor. Because what we have here is 1 times A. Okay, so the one factor is 1, which is the numerical factor, and this is the variable factor. Okay, if I have 2A, okay, how many factors do I have? 2. Is that not it? 1 being numerical factor 2, and the other one being the variable factor A. Okay, so in the same thing, the same way, if you look at this, if you come to this, we are saying that if I have root of what? Root of 2. Okay, this has 2 factors, which will be 1 and root of 2. Is my point well made?
Yes, please come again.
Okay, I said every number from where I came from. Okay, this is 1 times A. So in actual fact, this one has 2 factors. Only that one of the factors will be 1. Usually 1 is a factor of every number. So we don't consider 1 to be a factor, usually, but it's a factor. You get my point? So in my explanation, I'm considering 1 as a factor and this also as a factor. Okay, with this one, automatically this becomes a factor and this is a factor, your usual one. So if I have root of 2, I know that any number that is, okay, standing alone, 1 is a factor of every number, you agree. That's why I'm treating 1 as a factor. So every number that you are giving, you know that 1 is a factor of it, and the number itself is a factor of itself. You get the point? So if for nothing at all, if I give you any number, you should be able to give me two, okay, factors of the numbers, of the number. So if I give you 3 and I ask you to find factors of 3, you should know that 1 is a factor of 3 and 3 is a factor of itself. You get the point? Okay, so if I give you root of 2, you know that this is a number. So 1 is a factor of root of 2, and root of 2 is also a factor of itself. So if for nothing at all, you know that you have 2 factors. All correct now?
Yes, please.
Okay, so look at what we have here. We said it is a set which has only one as a rational factor. So you have 2 factors. You can see that 1 is a rational factor. 1 is a factor, but it's rational. But root of 2, the other factor that you have here is irrational. Remember, I said that all sets are irrational numbers. And when you did, okay, the real number system, you got to know that, okay, all sets, okay, all square roots or square roots of numbers, provided what you have here is not a perfect square, will be irrational. So your factors, 1 will be rational, 1 will be irrational. But the rational one should be 1. Okay, so it means if I have maybe 2, oops. Okay, if I have 2 roots of 2, okay, how many factors do I have here? I have 2 and what? And root of 2. Do you agree?
Yes, please.
Okay, between these 2 factors, 2 is a rational number, right? Two
Yes,
is a rational number. Okay, and root of 2 is what? Is irrational. Now the 2 that you have there is not 1. Okay, so once your rational number ceases to be 1, okay, then it means whatever you have there, the set that you have there ceases to be called a pure set or a complete set. Because for a complete set, the coefficient, which is what is multiplying the set, okay, must be what? Must be 1. So simply put, a set with a coefficient of 1 is what we call, okay, a pure set. So if you have any set whose coefficient is not 1, then it ceases to be what? A pure or a complete set. Okay, so if it's not a complete set, then what is it? Or a pure set, then what is it? It becomes, okay, the next type of set. So a set which has a rational, which is a mixed set, a set which has a rational factor other than 1. So you have a factor, okay, one being irrational, the other being rational. But we are saying that the rational one, if it is the rational factor, if it is strictly 1, it is a pure set. If it is not 1, but any other number, then it makes your set that you have there a mixed set. Is my point well made?
Yes, please.
Okay, so you can see in this example, okay, how many factors? Who said I should come again? Let me see if I can, when you understand, and I know that the rest, they also understand. Okay, which of my professors asked me to come again?
Please, Leslie.
Leslie, okay, so it means all that the question that I'm going to, I will direct it to you. Okay, how many factors do you see in this example? How many factors?
Please, 2.
Okay, which are?
3 and square root of 2.
Very good. Okay, so 3 and square root of 2. You know that your first factor, 3, is a rational factor. Your second factor is irrational. Okay, but we said that for your set to be pure, the rational factor there should really be 1. Okay, so if it is not 1, then it will be any other number. So when it becomes any other number, then you move from pure set to what? Mixed set. So for the mixed set, your coefficient, okay, of your set should not be 1. It should be any other value apart from 1. You get it?
Yes, please.
Okay, so it means if you know the pure set, indirectly you know what the mixed set. So another way of stating the mixed set would be, okay, you can write that is a set with a coefficient, okay, of not what? 1. Or a set whose coefficient is not what? 1. Okay, and that will give you so you can see that if you look at the coefficient of this set, root of 2, it is 3, not 1. Root of 3, it is 5, not 1. Okay, root of 11, it is 1/3. So the coefficient here, none of them is 1. So making it what? what we call a mixed set or mixed sets. Is my point well made now?
Yes, please.
Okay, so now we move on to the next one, which will be the next type, monomial or simple sets. Okay, when you hear monomial, what comes to mind? Mono.
One.
One. Okay, so one. So basically, okay, a monomial set, when we say a monomial expression, you know there's an expression containing only one term. So if I say monomial set, it will be a set containing only one term, as simple as that. Okay, math, the language usually, okay, is similar. Okay, so you should be able to, like I said, I gave you rational numbers. And you said when you are dealing with functions, it will be rational functions. If you are dealing with expression, it will be rational expression. It's the same thing. Okay, all right. So now what do we have? A set which has a single term only. So a set with only one term. And this will give you a monomial set, a monomial set, a monomial set. However, okay, this monomial set, let me see. The first set that you have here, is it a pure set or a mixed set?
Pure set.
Pure set. What about the second one?
The mixed set.
Mixed, same as what's the third one, because it's only the first one that, okay, the set has a coefficient of 1. The rest, okay, they don't have. So the last two becomes pure, the first one. The last two becomes mixed, the first one's pure. Take notes. So quickly, let's move on to the next, okay, one. So once you know monomial, you should know binomial. So mono is 1, bi, okay, you know is what? Is 2. So binomial, we know we are going to deal with a set containing 2 terms. Okay, as simple as that. And you know that terms will usually be connected by either addition or subtraction, but usually we'll say that they are connected by addition because you can always treat subtraction as addition. By that, this is what I mean. If I have A plus B, okay, I know this is a term, this is a term. Okay, if I have A minus B, I can treat this one as what? A plus minus B. Is it not the same?
Yes,
so
please.
you can always treat subtraction as addition. So anytime we are talking about, okay, what do you call it? Terms, we use, okay, addition. Because we know that though subtraction can be used, we can treat subtraction as what? As addition. So take note. So binomial, algebraic sum or difference of two sets, or a set and a rational number. So this is it. Okay, look at what we have here. We have two sets, obviously. So monomial set put together, you get a binomial set. Okay, monomial set put together here with negative, but we know the same as plus minus this. Okay, so binomial, 2 terms. But if you look at these two, the first one is not a set, am I right?
Yes.
Okay, the second one is a set. Okay, so whenever you add a set and an unsaid, okay, indirectly, if you add a rational number and an irrational number, you definitely get an irrational number. You agree?
Yes.
Okay, very good. So in this case, okay, the fact that you are not dealing with each term being what a set doesn't mean you cannot call this or label this as a binomial set. Okay, what is important is that one of your terms, at least one of the terms, okay, must be a set. Because immediately I see a set in it, then it means all that I have here is a set. Just as when you have a rational number, irrational number, you know the overall result will be irrational. So we say that what you have there will be irrational. However, this will be irrational by a special irrational, which will be there. So take note. Okay, and same for this one as well. Once a set is in play and you have two terms, okay, whether both are set or one is a set, what you have there becomes a binomial set. All correct?
Please.
Okay, so remember we said another name for monomial set is simple. So if it is not simple, it will be compound or composite. Do you agree? Okay, so if we define simple as what? Okay, a set with only one term, then it means compound or composite will be a set with more than a term. Okay, so you can see that a binomial set is also a compound set. Only there is a special compound set with two terms, so we give it a binomial. So if it becomes 3 terms, we can call it a trinomial set. You get the point?
Mr. Akman,
Yes, my prof.
please, is binomial sets and compound sets the same?
No, they are not the same. Binomial set is a subset of compound sets. So you can see if you read what you have here, here I said 2 sets, but here I said 2 or more. Can you see? This can go beyond 2, but this cannot go beyond 2.
Okay, yes.
You get it? Okay, so a binomial set is a subset of what? Okay, that's why I said a binomial set is a special form of compound set with only 2 terms. So I can also say that a trinomial set is a compound set. Only there is a compound set, I'm giving it trinomial. Okay, because it will contain 3 terms, with at least one of the terms, okay, being a set. Is that okay?
Please come again.
Okay, when you mention tri, what comes to mind?
3.
3. Okay, so obviously. So if I mention trinomial in expression, you know, usually you use omia, nomia, okay, what have you. So if I have trinomial, okay, it means I'll be dealing with what? 3 terms. Okay, but because I'm dealing with sets, okay, what will make my expression a set until the expression contains, okay, one of the terms being what? A set, or contains the square root sign with what you have under the radical sign, okay, or radical not being a perfect square. So it means if I have this, okay, root of 2 plus root of 3, okay, plus 4. How many terms can you see here?
3.
3 terms. So it makes, okay, this is a trinomial already, 3 terms. However, because we have said there, okay, instead of saying trinomial, we qualify it, okay, to be more specific. So it becomes what? A trinomial set.
Mr. Akman.
Yes, please.
So a trinomial set can be a compound set.
Yeah, it is. Because remember we said compound, okay, it should be 2 or more. So it should be 2 terms, 3 terms, 4 terms, 5 terms, and more.
Yes, please.
You get it? So if it is 2, it is still a compound, only that we give it a special name binomial. If it's 3, okay, it is still a compound, only that we give it a special name trinomial, only that I didn't mention it here. So by inference, you know, it's my point well made, or by extension, you should know that. So you can see that this is a binomial set, but it's still a compound set. This is a binomial set, still a compound set. How many terms do you see here? 3. A trinomial set, it is still a compound set. All correct?
Yes, please.
Yes,
Okay,
please.
great. Okay, so now let's look at like or similar was said. Okay, in math, anytime you are dealing with algebraic expression, okay, how do you say that 2 terms are alike? How do you make the determination? Under what situation can we say that 2 terms are alike? Okay, any ideas, any suggestions, any answers? My professors, today you are not responding. Okay, Prof. Paulette.
Please, if they have the same denominator.
The same denominator, then they will be alike. So it means if your expression, okay, is not a fraction, then you cannot say that they are alike, because once denominator comes in, then it means you are dealing with a fraction.
Please, this in fractions.
In fractions, okay, no, I said algebraic expressions in general. Okay, let me see who else. Okay, Prof. Prof. Mame, yeah, Ochere.
In algebraic expression, two terms are said to be alike if they have the same variable.
Just the same variable? Okay, I will give you 5 out of 10. Okay, one of the conditions given. Okay, let's see if another person can add. Okay, Prof. Lillian.
They are said to be alike when they have the same variable or radical.
Okay, so I want to control any different answers.
They are said to be alike if they have the same variables and exponents.
Perfect. Okay, so same variable, same exponent. Otherwise, if you say same variable, let's say if I have 2x, okay, and 2x squared, then you can say that these two terms are alike because they contain the same variable x. You get the point? But these two are not alike. They will be alike when they contain the same variables and what? And the same exponent on the variables. Okay, so that is how you determine, okay, like terms in algebraic expressions. Okay, now let's see how we determine like terms in sets. Okay, how do we identify sets to be alike? Okay, so two or more sets are, okay, so you let me make it simple because of time. So for two or more sets to be alike, they should have the same radicand. As simple as that. So we use the radicand to determine only the radicand to determine, okay, whether the sets are similar or alike. Is my point well made? Or I should come again? Okay, so it means if I have roots of 3, any set that is alike to this will also have roots of 3. The radicand will be 3. Okay, neglecting the coefficient, because you know, if I have x, okay, and another term which will be alike to this expression x will also have x there, only that the coefficient can change. Okay, but as for the variable and the power, it shouldn't. Other than that, immediately the variable changes or the power changes or both, any of them changes, please, you should know that you are not dealing with like what's said. So that's the more reason why here we are saying the example, root of 2, fifth root of what? Oh, sorry, this is not fifth root of, this 5 times root of 2, 8 times root of 2. These 3 are like, okay, sets, because all of them, they have the same radicand. Okay, 2, 2, 2. Okay, all right, so indirectly, if I have a set, okay, any set that will be alike will be a multiple of that set. Will be a multiple of that set. Please take note. So if I have root of 2, okay, I can have root of 2, which is alike, okay, to root of 2. I can have 2 roots of 2, which is alike. I can have 3 roots of 2, multiples of that. Take note. Is my point well made? Okay, if that's the case, then now let's go and look at, okay, reduction of sets. Okay, reduction of set. So to reduce a set, okay, means to write or express it in its basic form. Its basic form. Okay, a set is said to be in its reduced or basic form if its radicand cannot be written as a product of a perfect square and non-perfect square. I repeat, a set is said to be in its basic form or its reduced form, its simplified form. Okay, if its radicand cannot be written as a product of a perfect square and non-perfect square. So indirectly, I'm trying to say that if its radicand does not contain a perfect square apart from 1. Okay, so that is, okay, its radicand does not contain a perfect square apart from 1. Okay, so take note. I think as a factor, so I think I should have closed this. Okay, I opened the bracket there, so I will do the editing, okay, later. Example, okay, so this is it. Root of 5, Okay, so obviously you can see that the 5 that you have here, okay, which is your radicand, apart from 1, which is a perfect square, it doesn't contain any perfect square factor. Let's come to 10, your radicand 10. Apart from 1, do you have any factor of 10, which is a perfect square? Hello, do you?
No, please.
Okay, and same for this. So assuming maybe I have roots of 20. Okay, my radicand 20, apart from 1, okay, can you have any other perfect square factor of 20?
Yes, please.
Which is
4.
4. Do you all agree? Please, do you all agree?
Yes, please.
Okay, so we know, okay, that because your radicand can contain or has, okay, another perfect square apart from 1 factor, it means the set that you have there is not in its basic form. So it means if you know, okay, the definition for the positive, which is the basic form, you know that of not in the basic form, the negative. Am I clear? Okay, Prof. Mia.
Please, I don't understand the square of 20. How can 4 go into it? I don't understand.
No, I didn't. I said look for the factors of our, for you to determine that the set is in its basic form or not. Okay, you concentrate on the radicand. What is the radicand here?
20.
The radicand is 20. So remember we said your radicand shouldn't contain any other factor apart from perfect square factor, I should say, apart from 1. So let's list the factors of, okay, 20. 1, 2,
2,
4.
4. Okay, you end here because you can see that 4 is a perfect square. So apart from 1, you have another perfect square factor of 20. Do you get it now?
Yes, please.
Okay, so once you have another perfect square factor of 20 apart from 1, then it means the set that you have here ceases to be, okay, in its basic form or in its reduced form. So it means it can be reduced. All correct? Okay, I want to hear yes from the person who said she didn't understand.
Yes, please.
Okay, great. Okay, so next time respond because it's because of you that, okay, I had to go back. So the question basically will be for you mainly. Okay, so you come to this. Okay, so now how do we reduce set if the set is not in its basic form? So to reduce a set to its basic form, okay, 1, this is what we do. Write the radicand as a product of the highest perfect square, and I have highest here, okay, for a special reason. Very soon you get me. And in books, they don't write highest. Okay, they will just write a perfect square and then perfect square. So any perfect square will do. But I am more interested in the highest perfect square factor of your radicand. Okay, so first of all, you have to write your radicand as a product of 2 factors. One of the factors should be a perfect square, and the other factor should be a non-perfect square. All correct?
Yes, please.
Okay, then after that, what do? We make use of the rule below. So this rule that we have here, the following rule. Root of AB, okay, root of the product of this, you know, from set, this will be the same as root of A times B, and that's the same as root of A times root of B. Do you agree? From indices.
yes, please.
Okay,
Yes,
so you use this concept of indices to simplify. Okay, and here, remember I told you one of the slides, when I mentioned the perfect square, I said, okay, I will, in one of my slides, you will see the perfect square. So when you multiply, note, when you multiply an integer times itself, the resulting product is called a perfect square, or a square number, or simply a square. So 0, if you first integer, 0 squared will give you 0, 1 squared will give you 1, that is 1 times 1. Where 2 times 2 will give you 4, okay, and so on, and so on. So these are all, examples of perfect squares up to what, 10. So, 1 squared up, 0 squared up to what, 10 squared. That's what you have there. Okay, so now let's move on to, how to reduce Z. Okay, so let's look at our first worked example. Let me check. Okay, so let's have our water break. When we come back, then we come and look at the first worked example. Is that okay?
Yes, please.
Okay, so
Yes.
I'm giving you 3 minutes. Okay, in 3 minutes, you should be back. So 5, so 7, maybe 8, 1, you should all be back. Okay. Okay, so welcome back from the water break. So here we have our first example on reduction of what? Of sets. So reduce the following set to their basic form. Okay, so this is what we have. And in maths, anytime you solve any question and you get a particular answer, immediately you realize that the answer can be reduced. You have to reduce it. You can't end with any expression that, can be reduced. Okay, so quickly, let's see how best to deal with the solution to this question. So as usual, the first thing that you write is solution. After reading the question, you are supposed to reduce this one to the basic form. So you underline basic form. Also, if it is not in the basic form, and we said the basic form will be a situation where your radicand will not contain any other number apart from what? Any other perfect square factor apart from 1. Okay, so now solution A. You extract what you are given, and what are we given? Okay, you are given roots of 8. And like I said, you can choose not to write the given. It's the same thing you have extracted. Then there's an expression you start with equal to. Okay, by now you should all know how to do this. Okay, so let's see. Okay, apart from 1, do you have any other perfect square factor of 8?
4.
Yes.
Okay, which is
4.
4.
Okay, so now we are going to write, 8 as a product of for the perfect square 4, and which number? 4 times which number will give you 8? 2. And you can see that 2 is not a perfect square. So now remember the first step, write it as a product of a perfect square and a perfect square. Very good. So that will give us root of what? 4 times 2. Do you agree?
Yes.
Okay,
Yes.
remember we said in indices,
Please.
anytime you are taking the square root of products of numbers, or factors, it will be the root of each of the factors. So I know this will be equal to, root of 4, times root of 2. Is that clear? Do you agree? Okay, please,
Yes.
who wants me to come again? Prof. Agnes.
Please, how is the first step different from the second step?
Okay, the first step, is different from the second step because the first step, you have your factors, the product together. The square root is affecting both. But the second step, the square root is affecting them individually. You get it?
Yes, please.
Okay, so at this point, we know because 4 is a perfect square, its root, you can easily get it. So root of 4 we know is 2. Okay, then it will be times root of what? 2. As we mature, some of the steps we can take out. This is the first example. So get the understanding first before, your presentation. So this will be 2 times root of 2. So anytime if I have 2 times x, I know that this will give me 2x. Is that not it? So 2 times root of x will give me 2 root of x. Is that clear? Sorry, 2 times root of 2 will give me 2 root of 2. Is that clear?
Sir, please can you come
again?
Okay, all right. Okay, you don't know the exact value of root of 2. Okay, so if you use your calculator, no, you don't use your calculator. Okay, so you don't know the exact value of root of 2. Okay, so if I have 2 times any quantity, it will be 2 the quantity. That's why I say if I have 2 times x, it will give me 2x. Is that not it? So if I have
Yes.
2 times root of x, that will give me 2 root of x. 2 root of x, take note, 2 root of x, okay, or 2 root of 2 is not the same as what? Square root of what? Of 2. Okay, you can see that this 2 is not an index, it is a coefficient. You get it? Points well made now.
No, sir, please. When you came down, you did it 2 times. I don't understand where the 2 came from.
Which 2? The first 2.
Yes, please.
Okay, the first 2 came from root of 4. Root of 4 is what?
2.
You get it? So all perfect squares, if you take their square roots, you should know.
Okay.
Okay, all right. So that will give us, then this one will be kept because we can't find, this is not a perfect square. The radicand is not a perfect square, so you can't find, okay, it's a set, so you keep it in a set form. Then you can, so at this point, you draw your conclusion. Therefore, are we all fine? Root of 8 is equal to 2 root of 2. Okay, so if you like, take your calculator and press root of h and root of 8 and call your answers for me. Okay, root of 8, mention your answers, those of you with calculators. So those of you, next time when you are coming to class, bring, it will give you have 2 root of 2. Yeah, so this is exactly how the calculator is programmed to give you this answer. So this is what goes on inside the calculator before this answer comes out. Exactly.
Yes,
So
please.
if you write root of 8, I mean, your calculator gives you 2 root of 2. How did the calculator get root of 2 root of 2? How did that become 2 root of 2? And this explains why. Okay, take note. And here we are not using our calculator. You can only use your calculator as a guide. Okay, but not, okay, to get your final answer, unless it's an objective question. Take note. Okay, so I saw a hand up, or you've changed your mind.
No, please.
Okay, go
Sir,
ahead.
please. Step 2 and step 3, are they necessary?
Step 2 and step 3. Yeah.
Yes.
Okay, then remember I said, as you mature, I will tell you the one that you take out. So I believe you want to take the wind out of my sail. All right, so as we move on, I will tell you, as you mature, I'll tell you the one that you can take out and it will not be possible. And you adapt.
Okay.
All right. Okay.
Okay.
So let's go. So now that you have agreed, okay, so B, what are we giving? Okay, root of 12. Okay. Apart from 1, okay, 12, radical, do you have any perfect square factor?
Yes, please.
Again, that will be what, 4, is that not it?
Yes.
Okay, so
Yes,
we
please.
are going to write, okay, the 12 as 4 times what? Times 3, exactly. 4 is a perfect square, 3 is an imperfect square. So the first step, okay, catered for. Okay, sort of. So now we know this will be equal to the second one too. I'm going to do it the same way. Going forward, I will take out, okay, the step that can be taken. Okay, so Daphne, from Daphne.
But please, the first step, the root of 4 times 3. Can you also change it to be maybe the root of 3 times 4? Like, can you turn it?
Yes, you can. No issues at all. Because multiplication is commutative. You get it?
Okay. Yeah.
Okay, only that usually we want the perfect square to come first. So that we can see that when you are multiplying, when you have 2 times x, it's prettier than x times 2. Okay, so that this will give you 2x straight away. The other one will also give you 2x anyway.
Yes, thank you.
You're welcome. That's the more reason why it's convenient to bring the perfect square term first. Okay, or factor first. Other than that, okay, it's not necessary. Okay, so in this case, again, we are going to get root of 4 times root of 3. You all agree, just as we agreed there. So root of 4 we know is what? Is 2. Okay, so times root of 3. So in effect, we are going to get the next step. I will draw my conclusion. Okay, so therefore, root of 12 will be equal to what? 2 root of 3. Do you agree?
Yes.
Okay, so now we are matured. Okay, we were able to work with one hand, the other hand, the other leg is here, first leg, second leg. So now we can run. Okay, so let's look at what? C. Okay, C, what are we giving? Root of 45. Okay, so now, okay, let's look at 45. Apart from 1, do you have any other, okay, perfect square factor?
9, please.
Okay, 9. That 9 is the only perfect square factor apart from 1. Is that not it?
Yes, please.
Okay, so now let's go. So it means we will write this one as the first step, which is you writing this as a product of the perfect square and non-perfect square. That is critical. Am I right? Are you following?
No, please.
So where exactly can't you follow?
You made a mistake with the 3.
I made a mistake. Okay, so it's intentional. So this is supposed to be 9 times what? So it means you are here with me. 9 times
5.
5. No, it's not 4.
5.
It will be 5. Okay, take note. Okay, so your next step, okay, which is this particular step, you can always do it mentally. So you know that to the root of your first, okay, factor here, which is a perfect square always. So that will give you, okay, 3. Okay, times root of this, so you get your 3 root of 5 straight away. So even at this point, you could have drawn our conclusion. So as you mature, we'll do so. So now, therefore, root of what? 45 will be equal to 3 root of what? Root of 5. And take notes, okay, this step you can skip. Where you write it as a product of the highest perfect square or a perfect square and non-perfect square, you can skip. After that, you mentally know that you take the root of them individually. So root of 9 will give you 3, then times root of 5 will give you root of 5, so 3 root 5. Then you can enjoy your calculation. All correct?
Yes.
Okay, great. Okay, so if you are all fine, then we have to go and move on to. So I think your question is now answered fully, right? You know yourself? The person knows. Okay, so you know who I'm talking to. Okay, so now D. Okay, so what do we have? Root of 50. So giving, okay, root of 50. Okay, so this will be equal to the perfect square apart from 1 that you can get from 50, a factor.
25.
25, so it will be 25 times 2, is that not it?
Yes, please.
Okay, so at this point, this gives us what? Root of 25, which is 5, times root of 2 is root of 2. You get it? Okay, so therefore, your root of 50 is equal to 5 root of 2. You shouldn't get it wrong because you can use your calculator to verify whether your calculator will give you the same answer. If your calculator gives you a different answer and you believe yourself more than the calculator, you move on. Otherwise, you go and check. Is that clear?
Yes, please.
Okay, Prof. Agnes.
From your explanation, you said we can place the 25, the opposite side of 2 by saying 2 times 25. So if I want to conclude, how do I know that is square root of 2 times 5 rather, or square root
Okay,
of 5?
it's the same thing. Okay, all right. So don't be confused. Okay, math is simple. Don't take your mind far. So if I have 5, okay, when you times root of 2, and I have root of 2 times 5, it's the same as me having 2 times x, then x times 2. Is that clear?
Yes.
Okay,
Please.
so if you have 5 times root of 2, okay, this will give you, this is a coefficient, so it will be 5, you write the coefficient first, your non-radicand first, followed by the set. So it should be 5 root of 2. If I have this will also give me, okay, 5 root of 2 is the same thing. I'll write just like this one. Will you write this one as x2?
No.
How would you write it?
2x.
2x. Okay, because this was what indirectly will be your variable. Then the constant indirectly. This is known. So it will come here and becomes what? So this will be the same as 2 root of 5. And this is 2 root of 5, the same. All correct?
Yes, please.
Okay, so you appreciate the concept better when we start looking at multiplication of sets. Okay, all right. So now this will be it. I'm seeing certain numbers. I don't know whether they are communicating with numbers. Okay, I'm normal specialist too, but I'm not able to connect what they are writing. Anyway, so let's move on, okay, to our next, okay, slide. So the last question there will be root of, okay, 48. So let's see what will happen. And I'll ask you to try the F. So E, okay, we've been given, okay, root of what? 48. Or you can ignore writing the given and just write root of 48. It's allowed. Okay, as you know, I've been doing that as well. So this will be equal to, so let's look at root of 48. Apart from 1, any other perfect square factors or factor?
16.
16. Well, why did you skip 4? Because 4 is also there.
Because you said we should find the highest perfect.
Very good. Okay, so you are making, so I will come to, okay, that. So you are going strictly by, okay, my advice. Okay, so for now, remember I told you that in books, they will just write perfect square, okay, without qualifying that to be the highest. So we are going to go by my approach, okay, or my steps. Let's see what will come out. And after that, we'll go and look at what the other one, where it is not qualified. So let's see. So it means with this one, you said the highest perfect square you can get from 48 will be what? Will be 16. Please, do you all agree? Highest perfect square factor. Hello, my professors, do you all agree?
Yes, please.
Okay, so it means I'm now going to write this one as root of 16 times what?
3.
Okay, times 3, very good. Okay, but we know 16 is a perfect square. Sorry. So in that case, I'm going to get what? I know what I'm going to write will land me at my answer. So I'm mature. So therefore, root of what? 48 will be equal to root of 4, root of 16, which is 4, times root of 3, which is what? 3. Sorry, which is root of 3. So I'll get 4 root of 3. Is that clear?
No, please.
Okay, so where exactly can I find you, my dear prof?
Please, the 4 is a perfect square, so
So you want to take the
I
square
don't
root again?
understand.
You want to take the square root again?
Yes, please.
No, you can say that. Remember we said it is the 16 that will be affected by the square roots. So it is 16 when affected by square root that transforms to 4. You get it?
Yes, please. Yes, please.
So here, this is not
Thank
under a square root, so you maintain it. Okay.
Yes,
I think
please.
you are
Thank
happy taking the square root. Please. So take it only once. Okay. All right. Okay. So that will give us what we have here. Okay. Now let's look at the alternative approach, which will be what maybe you see. Okay. Now, the alternative approach, what am I giving? I've been giving root of 48. Okay. You know that one perfect square factor apart from 16 is 4. Do you agree? So I'm not going for the highest perfect square. So I'm going for 4. So it will be 4 times what?
12.
12. Okay, 12. Is that okay? Do you all agree?
Yes.
So you've still written what you have there, your radicand there as a product of a perfect square, which is 4, and then perfect square, which is 12. So indirectly, that step catered for. Okay, now we know this will be equal to root of 4 times root of 12. But root of 4 we know will give us 2 because 4 is a perfect square times root of 12, which will give us root of 12. Okay, so you can see that here, can we end here?
No,
Okay, why?
because the number under the radical sign can be broken down.
Okay, so it means I want you to use the language because the set is not in its basic form. It can still be reduced. You get it?
Yes, sir.
Okay, so the point is, if you don't take the highest perfect square, okay, and there is another perfect square bigger than your choosing what perfect square, then it means you have to do more reductions before you get your final answer. Your results, if you don't pick the highest perfect square, okay, your first result will not be, the set will not be in its basic form. So that's why it is advisable to pick the highest perfect square so that straight away your answer will be in its basic form. Is my advice well taken? Well noted.
Yes, please.
Okay, so in this case, you don't end here. So it means you are now going to continue. So look at the volume of work. Then you write this as 2 times. You come and reduce this one to which will give you 4 times what? 3. So this will give you 2 times the 4 roots of 3 here. I mean, 4 times 3 here. This will give you root of 4, which is what? 2 times root of 3, which will give you root of 3. Is that clear? Are you following?
Yes, please.
Then now you come and multiply the non-radicals. So it will be 2 times 2, which will give you 4. Then you keep your set. Okay, so just like root of 3. So just like you have 2 into 2x, that will give you 4x. So your x is the set, which is root of 3. And you can see they're the same as the, however, look at the volume of work. So obviously this method will not be ideal. Don't go for it. Always go for the highest perfect square. All correct?
Yes, sir.
Okay, so if you understand, then I will leave this one. You try this one later. I want us to move on to our next concept. Maybe, okay, so let's see. Okay, we are going back. How to go back. Okay, so expressing sets in basic form as pure sets. Sets in basic form as pure sets. Okay, so this is the reverse process of what expressing sets in basic form. So, you know, we are reversing the process. So to express or write any set of the form A root of B as a pure set, and as a pure set, we said the coefficient should be what? Should be 1. Is that not it? Remember when I introduced you to the pure set, we said in terms of the types, okay, a pure set is a set with the coefficient of the set there being what? 1. Okay, with the factor, the rational factor being what? 1. All correct?
Yes, please.
Okay, so here you'll be given set with a coefficient not being 1, and you'll be asked to make the coefficient 1. So we make use of the rule below. So if I have this, this is the rule. You can see that any coefficient that came out here, remember from what we've been doing, okay, we took the square root of a certain number to get this result. So initially this one was a square number inside, or square of a number inside. Before we took the square root, okay, and it became this A. So if I'm taking it inside, okay, because I want the coefficient to be 1. If I want the coefficient to be 1, I don't divide. If I divide still by A, still my coefficient will not be 1 because I will get 1 over A. However, when you are dealing with expressions, I've told you, if you divide through expressions, you change the expression altogether. Because if I have 2x and you divide by 2, you get x. This and this, are they the same expressions? Are they, is 2x the same as what? X?
No.
No. So you always avoid dividing through by, okay, a constant in expressions. I've told you this, as well as variables. Okay, however, in equations and inequalities, we can divide by a constant, but not a variable. So for variables, none of them. But for constants, only equations and inequality that we can divide or multiply. That's just by the way. So here, you just have to go back. So the point is, if let's say I have 2 root of maybe 2. Okay, you can see that this 2 was a square of a number. You remember, it was a square of a number that we took the square root before it became 2. So if I'm taking it back, then it will go inside as a square of a number. So 2 squared, then times the 2 that you have there. So I'm using letters to represent. So this is a general, okay, rule. But, okay, out of the general, then we can get the specific rules. Is my point well made, or I should come again? Okay, so here the point is any coefficient that goes inside, okay, or becomes a radicand, that will go and be under the square root must be squared, because it was squared inside or under the square root before it came out as a non-square, because you took the square root of it. Okay, so if you get it, then I think we can go and look at, okay, the following worked example. Okay, so write the following set as pure sets. So all the sets here, you can see that their coefficients are not what? 1. So it means they are not pure sets. So if they are not pure sets, what kind of sets are we talking about here?
Mixed.
Come again. What type of set?
Mixed sets.
Mixed set. Please take note. You can also say impure sets. It's the same. Okay, so if it is not pure, the opposite of what? Okay, pure would be what? Impure. You get the point. Okay, so only that I introduce you to. Okay, mixed is the same as impure. I usually use mixed. So let's see how best we can move from the mixed, okay, or the set unique basic form to the pure form. Very easy, so easy. Okay, indirectly, it seems the A, we've done it. So when you read the question, you are supposed to express this as a pure set. So until the coefficient becomes 1, we don't end. Okay, because we know what pure sets are. So solution, that's what you write first after reading the question and underlining the salient part. Then you extract. So this time I won't write given. I'm going to write the 2 root of what? Root of 2. Is that clear? Which you can do so as well. So this will be equal to, we know the tax. Okay, we have to write this as a pure set. So it means the coefficient will be 1. This is making the coefficient not 1, but this was under the square root, then it came here. So we have to take Zacchaeus' words back. Okay, so we have to take this one back. So we are going to write this one as what? If this one goes back, it becomes 2 squared, then times what? 4. Sorry, times 2, forgive me. Is my point well made?
Please come again.
Okay, remember when you had, if I have maybe root of 4 times 2. Okay, this 4 is a perfect square because it's the square of what? 2, so it's 2 squared, is that not it? That's why you were able to take the square root of it and it became 2, root of 2. So if this is going inside, okay, or going to its original position, which is what? Appearing as a radicand, then when you take it back, you have to square. Because once it's outside, it means you've taken the square root already of it. You get it?
Yes, please.
Okay, so in this case, this is going to give us, as you mature, like I said, you take some of them. So this will give you, okay, 4 times 2. Okay, which in effect will give you root of what? 8.
8.
Okay, so that becomes the pure set of, okay, form of 2 root of what? 2. Okay, so therefore, okay, 2 root of 2 is equal to root of 8. So you can see that indirectly we are going back. Is that clear? We'll do more, maybe 2 more. Okay, then I think you'll be in the best position. The second one too, I'll do it, okay, not the matured way. Okay, so let's go and see the B. Okay, so all the unnecessary steps will be, okay, I usually start with giving, so I am programmed. So 2 root of 3. Okay, so this will be equal to root of, so the 2 will go inside and becomes 2 squared. So I know that it will be 4. Okay, let me deal with this systematically as we mature. Okay, times 3. Okay, then this will give us again root of what? 4 times 3. Okay, so your next step becomes your answer. So you can draw your conclusion there. Therefore, 2, sorry, root of, therefore 2 root of, therefore 2 root of what? 3 will be equal to root of what? 12. All correct. Are we fine, my professors? Is everyone fine?
Yes.
Okay, very good. Then now the D, sorry, the C, I will handle that maturely. Okay, so what am I giving? I've been giving, okay, 3 root of 5. So I know this will be equal to, the 3 will go inside the square, root, and it will be a square of 3. So square of 3 will give me 9, then times 5. So I'm going to get, therefore, my 3 root of what? 5 will be equal to 9 times 5, which is what? Root of what? 45. All correct. I guess we are all fine.
Yes.
Yes.
Okay, so then another matured way for the D, then the E, I won't touch it. Okay, so giving, and what am I giving? 5 root of 2. Okay, so this will be equal to root of, the 5 will go inside as a square of 5. Square of 5 is 25. Okay, times what? 2. So that will give us root of what? 50. You draw your conclusion here. So you get a point. So your conclusion can be drawn, okay, here as well. All right. So I guess my point is well made. Any questions at this point? Hello, my professors. Any questions at this point?
No.
Okay, so it means you are doing well so far. So very good. We thank God. Okay, so now let's see our next concept. Okay, the algebra of sets. Okay, the algebra of sets. Let me see whether time will allow us. Yes, at least let's deal with what? The addition, okay, and subtraction of sets. Okay, so remember I said that's my target. So when we say algebra of set in maths, when you mention algebra, okay, we'll be talking about addition, subtraction, multiplication, then division. However, I will combine the first two together and the last two. Okay, so let's see. Okay, so A, addition and subtraction subtraction of sets. Okay, so to add or subtract sets, these are the rules. Okay, 1, check or determine whether the sets are alike. Okay, so if you don't know how to make the determination that sets are alike, in algebra, you know, in algebraic expression, before you can add expressions or subtract expression, the expressions must be alike, true or false.
True.
So in the same way, before you can add or subtract what set, the set, okay, which will be your expression, must be alike. And how do we determine that the sets are alike? We said they should have the same radical on the face of it. Is that clear? Okay, then after that, okay, this is what we do. We add or subtract the coefficients and attach the common set factor. Okay, so maybe I will use the example there to deal with it. So rule 1, the first rule here is for addition. The second rule is for subtraction. So if I have a set, a root of b of the form a root of b plus c root of b, and you can see that here, this is also root of b, because I want my radicals to be the same so that the set will be alike for addition to be possible. Other than that, addition will not be possible. Okay, so what did we say we do? We add what? The coefficient. So it will be the coefficient of the first set, which is a, plus the coefficient of the second set, which is c. So it will be a plus c. You put the whole of that in brackets, because if the bracket is not there, then it means the c that is only going to be affected by this. So it will be a plus c in brackets. Then you keep your common set factor, and your common set factor here, there is a set of root b, a set of root b. So you attach what? That was said, root b. So specific example, if you look at this, okay, 3 root of 2 plus 4 root of 2. These two sets, are they alike? Are they?
Yes.
Okay, they have the same radicand. So once they are alike, then it means we can combine by either adding or subtracting. Okay, so in this case, if you are adding, which is the situation here, it will be a coefficient 3 plus a coefficient 4. Okay, you put them together, then you keep your common set root of what? However, okay, you can always ignore this and move from here to here straight away. Because in your normal algebra, if you have 2x plus maybe 3x, what would this be equal to? This week 5x, and you can see that because it's addition, okay, the 5x is coming from the 5 that you have there, it's coming from the addition of 2 and what 3, then you keep your x. Is that not it?
Yes.
Okay, however, you know, when you realize that you are adding the coefficient, you added the coefficient what mentally. You didn't come to write, okay, 2 plus, you never write this 2 plus 3, then you put and you write your x. You always add the coefficient mentally. The result, then you attach your common variable, in this case, our common set. So you can move from, like I said, you can move from this to your answer straight away whenever you are combining coefficients in terms of addition and subtraction. So it's the same idea. This time around, you subtract the coefficients. So it will be a minus c in bracket, then you keep your set. Okay, same for, so if I have 6 roots of 3 minus 2 roots of 3, they are like sets, so I can combine, whether be it addition or subtraction. So now I'm subtracting. So it will be my coefficient that I will subtract. So it will be 6 minus 2, which will give me 4. Okay, then I will keep my set root of what 3. So I can move from here to my answer straight away without going through. This will be done mentally. That's 6 minus 2. All correct. Okay, so on that note, let's go and look at what word examples. Okay, so yeah, some of the questions will be a little tricky, so you have to be on guard. Okay, so let's look at the first one. So simplify the following. Okay, so A, question solution. So questions are normal. This time around, you have a major question number 1. Then A. Okay, what are we giving? You can write given, or you can write 5 roots of 3, okay, plus 2 roots of what 3. In any case, this was what was given. It's an expression, so we start with equal to. Never should we start with what the implication sign. Am I clear?
Yes, sir.
Okay, so obviously these two sets are alike. Okay, they have the same radical in the terms. So once they are alike, then it means we can add. Okay, so if you're adding, you add the coefficient. So it will be 5 plus 2. Please do it mentally. Write a 7. Then you keep your root of 3. Okay, so now therefore, your 5 roots of 3, okay, plus 2 roots of 3 will be equal to, okay, 7 roots of 3. All correct? Okay, then let's quickly move on to B. Okay, B. I should come again.
Yes, please.
Okay, all right. Okay, so I said, okay, this one is even just like the illustrative example, okay, by introduction. So in this case, 5 roots of 3 plus 2 roots of 3. Remember we said once they are alike, anytime you are combining like terms, even in algebra, you combine their coefficient. Combination will be by adding or by subtracting. So you add the coefficient of the terms or term. So in this case, it will always be terms anyway. This plus this will give you 5 plus 2, your coefficients. Coefficient here is 5, coefficient here is 2. Okay, so if you add, that will give you 7. Then you keep your common set. So it's like 5 oranges plus 2 oranges. That will give us 7 oranges. You get it?
Yes, sir.
Okay, so that gives us what we have there. So same, you go to, okay, I'll write given. Okay, so just for you to know that you can ignore, you can write. Then 7 root of 5, okay, minus 3 root of 5. Okay, so these two terms, are they alike? Hello, are they alike?
Yes, please. Yes,
okay,
please.
so once they are alike, then it means we can combine. Okay, but here we are combining by subtracting. So we are going to get 7, the coefficient 7 here. The first coefficient minus the second coefficient 3. 7 minus 3 will give us what? 4. Okay, then you keep your cell root of what? 5. So 7 oranges minus 3 oranges will give you 4 oranges. Is that clear?
Yes, sir.
Yes.
Okay, as simple as that. Okay, now let's do the C. The C contains 3 terms. Okay, so C. Okay, you can have more than 2 terms anyway. So by extension, okay, we should be able to deal with it. So what am I? 3, okay, sorry, root of 2 plus 5, root of 2, then minus what? 4, root of 2. So one question combining addition and subtraction or subtraction. So now what do? We know all 3 terms are like sets, true or false?
True.
True. Once they are like said, then we know we can combine them. Okay, but when we are combining, we combine the coefficients. What's the coefficient of the set, the first set?
1.
1 is simply understood to be there. Okay, we don't write it. So it will be 1. We are combining the coefficient, just as if I give you maybe 2x minus x plus 5x, you know what to do. Okay, so in this case, it will be coefficient 1 plus the coefficient 5 here, which will give us 6, minus coefficient 4, that will give us 2. All correct. So if you combine all the 3 coefficients, you get 2. Okay, then you keep your set, which is root of what? 2. Is that clear? Hello, is my point well made, my professors?
Yes.
Okay, great. So at this point, you come and draw your conclusion comfortably. So plus 5 root of 2 minus 4, okay, root of 2 is equal to 2 root of 2. Feed your calculator with the whole of this, or even what, and cross-check with your answers. You see that you get the same result. Okay, now let's move on to D. Okay, these are carefully selected questions. So D, what are we giving? Okay, that is root of 12, okay, minus 5 roots of 12. Okay, so this will be equal to, okay, can we combine them straight away? Are they like sets? On the face of it, are they like sets?
Yes.
Okay, so that will give us what we can combine. They have the same radicand of 12. So that will give us the coefficient here 1 minus the coefficient here 5. So we are going to get what? Minus 4, am I right? Then root of 12. Is that clear?
Yes, please.
Okay, so well, can I say that therefore this is equal to this?
No.
Okay, why?
No.
It's not in the basic form.
Very good. You
Yes.
are speaking the language. I like that. Okay, so you do not leave, okay, any set which is not in its basic form as your final answer, or better still, you don't conclude with a set which is not in its basic form. So it means the set there, root of 12, we can reduce it. So we continue to reduce that. Is my point well made? So before you draw your conclusion after combination, check whether the set, your result, is in its basic form. If not, you go and reduce it. Okay, so now this will be equal to minus 4. We are going to reduce this, and that will give us root of what? 4 times 3. Okay, we are experts now in reduction. So minus 4, we know I'm going to put it in bracket. This will give us what? 2 root of 3. Do you agree?
Yes, please.
Okay, so in effect, I know my next step, if I multiply, I will end up getting my answer, my final answer. So that step, I will draw my conclusion. Okay, root of 12 minus 5 root of 12 will be equal to, so it will be minus 8 times 2. And that will give, sorry, minus 4. I'm saying the answer. Minus 4 times 2, and that will give us minus 8. Then you keep your root of 3. All correct, or if you want me to come again, you can still let me know. Okay, who wants me to come again?
Please come again.
Okay, from where? Don't wait for that. I've told you at a particular moment that you don't get it. Okay, let me know. Please, from where?
Please, the third step.
The third step, okay. All right. Third. So 1, 2, 3 here. Okay, so you know, you understand this. So you can see that this one is minus 4 multiplying the whole of this. Is that clear?
Yes, sir.
Okay, so once I'm going to simplify this, you know how to simplify this. Okay, so that will give us the root of 4, which is 2 times root of 3. So this is it. If you don't bring the bracket, you know that this is multiplying. Okay, let me ignore the bracket and let's see what will happen, whether the meaning will be the same. Okay, I'm going to remove the bracket. Okay, let's see. If the bracket goes, okay, what will be what you have there? It's reading minus 42 root of 3. Is that not it?
Yes, sir.
Okay, which is not what you want to put across anyway. So it becomes convenient and appropriate for us to put it in what? In brackets. All correct?
Yes, sir.
Okay, so I think now you are fine, Abby.
Yes, sir.
Okay, so now we should be good to go. So this should be in brackets, like I indicated. So it will be this time, like I explained. If I have 2, okay, times maybe 3x, I know that the coefficient will multiply, and that will give me 6 what? X. Okay, so I'm going to get minus 4 times the 2 rather. The non-radicals will always multiply. Okay, so minus 4, which is a non-radical, 2, which is also a non-radical, will multiply. And that will give you your minus 8. Then you keep your set root of 3. So after there, then we can move on to E. Let me see whether my time is almost. We can do at least one more. Okay, so let's look at E. Okay, so E. Okay, what are we giving? We've been given root of 12, okay, minus 5 root of 3. Okay, please can we add them? Are they like sets?
No.
Okay, can we combine? So it means here we can combine, right?
Yes, please.
Okay, in fact, on the face of it, we can combine. So please take note, like I said, the questions are carefully selected for you to know all the tricks. Okay, so here, this is what we need to do. Okay, the first one here, we said the trick is after combining, check whether it is in the basic form, your result. If not, you do change it to the basic form. Here, on the face of it, you cannot combine. However, instead, before you can comfortably say that the sets are not in their base, are not compatible in terms of you adding, meaning are not alike, make sure each set is in its basic form. So when you realize that the sets are in their basic form, that is when you can, and I repeat, that is when you can convincingly say that they are alike or not. Am I clear?
Yes, please.
Okay, so assuming I have this set, root of 5, okay, plus root of 3. Okay, this set, is it in its basic form? Is this set in its basic form?
Yes, please.
What about this one?
Yes, please.
Okay, so now let's look at the radical. They are not the same, so you can say comfortably that, okay, they are not what alike. So they are not compatible in terms of addition and subtraction. Now, if you come to this, okay, is root of 12 in its basic form?
No.
No. Root of 3, this is the set. Okay, is it in its basic form?
Yes, please.
Okay, the set here is in its basic form, the whole of this. So in that case, you can see one is not in its basic form. So you cannot comfortably say that, okay, just on the face of it, they are not what? Compatible. They are not alike. However, you know the trick, you have to make sure. So let's go and transform or reduce the one that is not in its basic form. Okay, take it to its basic form. So that will give us root of what? 4 times 3. Is that clear? Then this one is already in its basic form. So we keep it intact. Okay, so now if you reduce this gives you 2 roots of 3. We are experts now. Do you agree?
Yes, please.
Okay, so after reducing the first set to its basic form, okay, look at your results. Are the sets alike?
Yes, please.
Okay, so it means, okay, initially the sets we could combine. Only that on the face of it, okay, directly, we couldn't do so. Okay, so at this point, we know we'll come and, okay, combine the coefficient by subtracting the second coefficient from the first coefficient. Okay, so at that point, when you do that, you land at your result. So I will draw my conclusion that therefore, root of 12 minus 5, root of 3 will be equal to what? 2 minus 5, and that will give us minus 3. Okay, then you keep your set, which is root of 3. All correct. So if you like, you can feed your calculator with that, okay, and you know that you arrive at the same answer. Is my point well made?
Yes.
Okay, so on that note, okay, the G here becomes your assignment. Okay, I'll put it on the platform anyway for you. So this is the only question for you. Now, next meeting, we'll do more of what? Of the algebra. We'll continue with the, what do you call it? The addition and subtraction. And after that, we'll move on to multiplication. Okay, so any questions before I finally bring the curtains down? Okay, so you are all fine. We thank God you are all fine. Okay, Leonard, is there anything that I said that was not said in your class?
No, please.
No, okay, so far everything. Okay, your presentation, everything. I just, sorry, I just want to know whether, okay, your being here was very useful. Okay, Prof. Agnes.
Please, can you skip back to the reduction of sets? I didn't write something over there.
Oh, okay. Okay, so if it's about going back, okay, so don't worry, I'll go back, but let me draw the curtains down, then I go back for you. Is that okay? Okay, so if you are all fine, okay, we thank God that you are all fine. And please, this is the foundation, so make sure you get it. If you don't get it going forward, you will struggle. Okay, so you ask questions the next time. Thank God for a wonderful and a successful meeting. God bless us all.